Have you ever felt like you're drowning in information, especially when it comes to AI? Like things are moving so fast, it's hard to keep up.
Absolutely.
But also like you want to understand the core innovations, not just like the hype.
Yeah, for sure.
So today we're going to try to do that. We're diving deep into a new approach to how language models um, understand and process text.
It's really interesting because it's a very fundamental part of how these models actually work. It's like the very first step in how they break down language. Like, think of it as understanding how like the brush strokes make up a painting.
Yeah,
And today we'll be focusing on this new method called SuperBPE.
super BPE. That sounds like an upgrade, right?
Yeah.
So for our listeners, the key concept here is tokenization, right?
Mhm.
So imagine a language model encountering a sentence.
Yeah.
Tokenization is like that first step where that sentence gets divided into these smaller units, these tokens, so the model can actually work with them. It's kind of like the first way the AI sees language.
That's exactly right.
And up until now, the standard way of doing this has been subword tokenization, often using an algorithm called BPE,
Byte-pair encoding, yeah.
byte-pair encoding. So BPE essentially learns to identify these common sequences of characters and then merges them into single tokens. But a key characteristic of traditional BPE is that it relies on spaces, white space, as that primary boundary.
Right.
So it learns tokens within those spaces between words.
Yeah.
Makes sense, right? Like ice cream might initially be seen as two separate things because of the space.
Yeah.
But this is where the research we're diving into gets really interesting. So this team of researchers from the University of Washington, NVIDIA, and the Allen Institute for AI.
Right.
Some pretty big names in AI, right? People like Alisa Liu, Jonathan Hayase, and Yejin Choi.
Yeah.
They kind of looked at this and said, hold on, is whitespace really that reliable as a linguistic delimiter?
Right. I mean, like, think about it like a simple phrase, like, by the way.
Yeah,
We write it as three words with spaces, but often it functions as like a single unit awaited transition. And so, like, BPE, because it's focused on these spaces, might tokenize it into three separate parts and lose that like cohesive meaning.
yeah. And this isn't just like an English thing, right? The research points out that like different languages express the same idea with totally different use of whitespace.
Absolutely.
So for example, the English spacesuit helmet, three words.
Yeah.
But the German raumanzughelm is one single word, no spaces.
Yeah, and that's just one example. I mean, imagine languages like Chinese and Japanese where they don't use spaces to separate words at all.
Right. So traditional BPE, when it hits those languages, is kind of stuck.
Right.
So our mission today in this deep dive is to explore this innovation behind Super BPE, understand why it might be a much better foundation for language models, and really by the end, you'll understand why this subtle change in how we process text at the beginning could have a huge impact.
Absolutely. And what's particularly interesting from the academic side is that Super BPE builds on the existing BPE algorithm, but it introduces this new two-stage pre-tokenization curriculum.
Okay, a curriculum. So it's like a structured learning process specifically for the tokenizer.
Yeah, exactly.
So tell us, what's the first stage of this learning process?
So the first stage is actually pretty conventional. It mirrors the standard BPE process. It starts by identifying these common token sequences within those white space boundaries.
Okay.
So this ensures that the model first learns those basic building blocks of the language, like, subwords or whole words. But at this stage, it's prevented from merging across those white space divisions.
Got it.
And this stage continues until the vocabulary size reaches a specific transition point.
Interesting. So it starts with a familiar approach.
Right.
It learns the components within what we consider words.
Yeah.
But what happens when it hits that transition point?
That's where the real innovation comes in. So after the vocabulary reaches that predefined size, they disable the white space pre-tokenization.
Okay.
And now, when the BPE algorithm looks for frequent adjacent token pairs to merge, it's no longer limited by those initial boundaries.
So now it can learn, by the way, as one single token.
Yeah, exactly. So it can identify and merge these frequently occurring sequences, even if they originally spanned across spaces, creating these superword tokens that represent, like you said, entire multi-word expressions.
And this, from like a technical perspective, it's just this small tweak to the tokenization algorithm.
Right.
It doesn't actually change the architecture of the language model or how it's trained, which is really remarkable.
It's really about segmenting the input text in a more intelligent way.
Right. So the goal here is to create these more semantically coherent units, capture, by the way, as one meaningful chunk, and make encoding text more efficient.
Ex-
So does it actually work?
Well, that's the exciting part. The research shows some pretty compelling results. One of the most impressive findings is the improvement in encoding efficiency. So when they kept the vocabulary size constant at 200,000 tokens, SuperBPE used, on average, up to 33% fewer tokens to represent the same text compared to traditional BPE.
33% fewer tokens. That's huge. So, like, what does that actually mean for someone who works with large language models? What's the practical implication of that?
Well, practically speaking, it means that SuperBPE can represent the same information with a smaller vocabulary, which can lead to faster processing and lower memory usage. And they actually visualize this in Figure 1 in their paper.
Okay.
It shows that as the vocabulary size increases for standard BPE, the encoding efficiency hits a limit. It just can't improve beyond a certain point because it runs out of useful words to create tokens from.
It's constrained by those spaces, right?
Exactly.
And Super BPE, because it can look beyond those spaces, it can keep getting better.
It can keep incorporating these multi-word units, which leads to constant improvement in encoding efficiency, even with larger vocabularies. And, they even quantified this. They had this 40-byte sequence, and they showed that Super BPE could encode it with just 7 tokens, while BPE needed 13 tokens.
Yeah. So it's like packing more information into each token.
Exactly. And what's also interesting is that Super BPE actually outperformed a version of BPE that didn't even use Whitespace pretokenization at all.
Oh, so it's not just about ignoring spaces, it's about this two-stage process.
Right. It highlights the importance of that initial subword learning phase.
So, okay, we have more efficient encoding.
Yeah.
But how does that translate to the actual performance of the language models?
Well, they did some really rigorous experiments where they pre-trained these massive 8 billion parameter transformer language models.
8 billion.
Yeah, and they kept everything else the same. The only thing they changed was the tokenization method, either BPE or Super BPE.
Okay, so isolating the effect of tokenization.
Exactly. And the results were impressive. The models trained with Super BPE showed a 4% average improvement across 30 different downstream tasks.
Wow.
This included things like question answering, mathematical reasoning, code generation, all sorts of tasks.
So a pretty broad range.
Yeah, and what's really notable is that on the MMLU benchmark, which is this test of like general language understanding.
Yeah, MMLU. It's tough.
Yeah, the improvement was over 8%.
8%, just from changing the tokenization.
Yeah, it's a pretty significant finding. It suggests that Super BPE can actually lead to models that have a better understanding of language.
That's really remarkable.
And if you look at the individual task results, they actually outperformed the BPE baseline on 25 out of the 30 tasks.
Wow.
And on top of that, these performance gains came with a reduction in computational costs during inference, so they were actually more efficient to run as well.
That's a win-win.
Right, so better performance and lower computational costs.
Okay, so another interesting thing that a paper talked about was this more uniform per token difficulty. Can you explain what that means?
Yeah, so what they found was that with Super BPE, the language model faces a more consistent level of difficulty when it's trying to predict the next token in a sequence.
Okay, I think I get it. It's like with traditional BPE, you have some tokens that are super easy to predict. Like maybe those common words, and then you have others that are really hard.
Yeah, and that creates an uneven distribution of difficulty.
So Super BPE is kind of smoothing that out.
Exactly. Because it can capture those multi-word expressions as single units, it forces the model to put in a more consistent amount of effort for each prediction.
Interesting. So are there any like practical implications of this?
Well, they looked at the bits per byte, which is like a measure of how surprised the model is by each token, and they found that Super BPE models had fewer predictions with extremely high or low bits per byte.
So it's more consistent.
Yeah, and this suggests that Super BPE might be better at predicting the more meaningful parts of language, the parts that actually require understanding.
Okay, so what about scaling? Like, how does Super BPE work with different size language models?
Well, they did some experiments with smaller models, and they found that if under trained situations, Super BPE generally did a better job at compressing the information.
Okay.
But when the models were overtrained, the results were a bit more mixed.
Yeah.
But overall, the Super BPE model that was scaled to match the computational cost of the BPE model tended to perform the best.
Got it. So it scales pretty well.
Yeah, it seems like it.
Okay, so the paper also looked at the actual vocabulary learned by Super BPE.
Right.
And they found some interesting differences there. Can you tell us about that?
Yeah, so one key difference was that the tokens learned by Super BPE were more evenly distributed in terms of frequency.
Okay.
So there weren't as many tokens that were super common or super rare, which could be a good thing.
Why is that?
Well, sometimes those really rare tokens can cause problems because the model haven't seen them enough during training.
Okay, so it's a more robust vocabulary.
Right, and they also found that SuperBPE made better use of its vocabulary. It needed a larger portion of its tokens to cover the same amount of data compared to BPE.
So the tokens are more densely packed with information.
Exactly.
Okay, one last thing that caught my eye was this idea of prompt boundary issues. Can you explain what that is and how SuperBPE might help?
Yeah, so this is a bit more technical, but basically with BPE, the way the prompt is tokenized can sometimes create these artificial breaks at the end of the prompt,
Okay.
and that can actually influence the text that the model generates.
Oh, interesting.
Yeah, and because SuperBPE can create tokens that span across word boundaries, it might be able to reduce these unnatural breaks.
So it could lead to smoother, more natural sounding text.
Yeah, potentially.
That's pretty cool.
Yeah, it's an interesting area for future research.
Okay, we've talked about the mechanics of SuperBPE, the impressive results, how it all works. But how does this fit into the bigger picture of language model development?
Well, tokenization is really a foundational element of language modeling, and it's something that researchers have been working on for decades.
Yeah.
The original BPE algorithm actually came from data compression back in the 90s, and it wasn't until relatively recently that it was adapted for NLP.
Yeah, and SuperBPE is like the next evolution of that, right?
Exactly. And it's important to note that there's a lot of other research happening in this area, like looking at multi-word tokens, multi-token prediction, even tokenizer-free language modeling.
Yeah, so there are lots of different approaches.
Right.
But what makes SuperBPE really stand out is that it achieves these big improvements without needing to change the underlying architecture of the language models.
Yeah, it's a much more practical solution.
So basically, SuperBPE is paving the way for more efficient and powerful language models.
Absolutely.
Models that can understand and generate more complex and nuanced language.
Exactly.
And it does all this while also requiring less computational power.
Right.
And what's really exciting is that SuperBPE is designed to be a drop-in replacement for existing BPE systems.
Yeah, that's key.
So it can be easily integrated into current workflows.
So the potential for widespread adoption is really high.
That's great. So for our listeners who are trying to stay on top of the latest advancements in AI, the key takeaway here is that SuperBPE is a major innovation in tokenization. It allows language models to learn more meaningful units of language, which leads to all these benefits we've been talking about.
Exactly, and it highlights how these seemingly small changes at a fundamental level can have huge ripple effects throughout the field.
Yeah, it's really amazing. And it makes you wonder, like, what other foundational assumptions are we making in AI that might be holding us back?
Right, and maybe this will inspire some of our listeners to explore SuperBPE in more detail or think about how this could impact other areas of AI.
It's definitely food for thought. So thanks for joining us on this deep dive into SuperBPE. We hope you found it insightful.
Thanks for having me.